We're at the University of Amsterdam for the Connecting Europe tour, and I'm here with
Christian Schaffner.
And Christian, can you tell me what you do here at the university?
Yes, I'm a professor in theoretical computer science. I have an office here in this beautiful building upstairs on the 6th floor. You can almost see it.
And what do you do as part of your job here?
Yes, I'm doing research. My own research is in the area of quantum cryptography. So cryptography you've probably heard about.
Yeah.
It's about like protecting data from attackers, how to encrypt data to ensure privacy, or how to authenticate data so that nobody can tamper with it. So that's kind of the general area of cryptography. And we throw quantum computing into the mix.
Where would you place cryptography, quantum cryptography, and cybersecurity?
Oh, I think this is going to be a growing area of interest. It used to be a very small corner, actually, in my own research. When I started studying mathematics in Switzerland at ETH, and I thought I would never do anything applied, because why would you as a mathematician? But I ended up being here working on stuff that is very relevant in practice.
And so how would you describe the cybersecurity and cryptography scene around Europe?
Europe is very active in this area of research. It's doing very well as well. So maybe I can explain you a little bit what the problem is. So the way we make sure information is secured at the moment, for instance on the internet, is part of it is protected by so-called public key cryptography. And the security of public key cryptography is based on some mathematical problems, like factoring large numbers and some particular problems. But it turns out that these problems are only difficult for classical computers, for normal computers. If we are at the point where we have quantum computers, so if good enough quantum computers come around, then we can actually attack this kind of cryptography and break these schemes. So that means that all the data we secure now with the current systems will actually be broken and read. And it's possible to read them if large enough quantum computers become available.
So you would describe these quantum computers as super intelligent computers who are way better than a normal computer?
You might think that, but that's not the case. In fact, quantum computers are going to be rather slow in terms of like their
processing power?
Not in terms of processing power, but in terms of like the frequency, the clock frequency. Say the heart rate of the machine is actually going to be way lower than of normal computers. But the trick is they're based on completely different physical systems. So usually in normal computers you work with zeros and ones, like with bits, and then bytes, and megabytes and gigabytes. But quantum computer is based on qubits, on quantum bits. And quantum bits have some funny features. Interesting. They can be, for instance, in a superposition. So they can be both 0 and 1 at the same time. This is what we call a superposition. Okay. And this allows to get way more computational capabilities. So you can do things that you cannot do on a normal computer, on a quantum computer.
And what would you say is the state of implementing quantum computing into our everyday lives?
I think that will take a while. So even the state of quantum computing in general, building the hardware for it is actually a very difficult task. There's a lot of colleagues in the Netherlands, but also in other places in the world working on this problem. But they haven't gone that far. So far the biggest quantum computers we have maybe 50, 60 qubits, quantum bits. And those qubits are far from being perfect, so they're very noisy, they make a lot of mistakes. And what we need to, for instance, break these cryptographic assumptions that I talked about before is like millions of qubits. So we're still very far away from that moment. But nevertheless, it could be that the development also goes like exponentially, as it often goes in computer science. And so we might be closer than what we think.
We were at the Nokia Research and Development Office in Antwerp, and they had a quantum safe unit in their research labs. Can you tell us more about that? Is it safe, or what does that even mean?
Yes, so this is referring to what we call post-quantum cryptography. So this is a new type of cryptography, and classical cryptography, so non-quantum, that remains secure against quantum attackers. So this is also one of the research areas that I'm working on, where you try to come up with new mathematical problems that are hopefully also hard to solve for quantum computers, and then make new cryptographic schemes that are based on this assumption instead of the one that we're using right now.
Previously, you had said earlier that it's good, it's going well in Europe. What did you mean by that?
Yeah, so for this type of new cryptography, this post-quantum cryptography, there was an international competition held to figure out what the schemes are that we should be using in the future. And so this has been going on for the last 5 years. And it turns out that the finalists, those schemes that actually will win this competition, it's more or less known now, the standards are about being written. And it turns out that these schemes have been invented in Europe. So even though this process has been coordinated by some American institution like NIST, the National Institute for Standards and Technology, the actual cryptographic schemes that the whole world is going to use have been invented by European scientists, among some colleagues actually from across the street.
Can you tell me more about these schemes? How are they being created? Is it connected to legislation as well?
No, I would say this is a discipline of what we call theoretical computer science. It's basically some applied mathematics. You have to think of people like sitting in their offices and writing stuff on the whiteboard and coming up with mathematical problems that are difficult to solve. So that's kind of to create the cryptographic scheme. Of course, in the next step, you actually have to do some engineering as well. You have to do a cryptographic implementation, which is notoriously hard. So people have to be very careful in programming and implementing the schemes in a way that they are secure, for instance, against side channel attacks. Now, there's advanced attacks that exploit, for instance, power usage of the system to figure out what the scheme does. So it's all of these steps have to be very carefully taken, and it's quite difficult to do it right.
Would you say there's a lack of legislation in the field of quantum computing?
So, maybe sticking to the post-quantum cryptography field, I think it's people have waken up because there's really a transition needed. So the schemes that we're currently using will not be secure anymore in 10 years, which seems to be or maybe in 15 years, whenever the quantum computer comes around, which seems to be far away. But in fact, there's the so-called store now or harvest now, decrypt later problem. The thing is that if you have data that you want to keep secure for, say, 15 years, for 20 years, like state secrets or maybe medical data, then you are in trouble already now. If you keep using the current systems, then the data will be decrypted when the quantum computer comes around. So the problem exists already right now. And in fact, to cope with this, we have to kind of create awareness, and that's a great opportunity
that's what we're here for.
To exactly talk to you, that people have to be aware that they have to change their cryptographic system to this new kind of post-quantum secure systems. And this sounds easy. Well, you just have to update the software. That's maybe still easy, but you also have to replace a lot of hardware. Think of, you have to replace all the smart cards that we're using, the access card that we needed to get into this building. They all have to be replaced with new systems. So this is going to easily take 10 years if we start right now, and we are not even close to actually starting. So in terms of legislation, it would be great to give this a push and to make people aware that actually have people, businesses, public administration, etc., to get started with this process.
This upgrading is happening right now as we speak. This is what the whole project is about, of Nomios, a networking cybersecurity company working with Nokia, who's got the hardware. They are coming together to upgrade this GÉANT network, which is all around Europe. So that is happening now. They are putting in the new tech to hopefully be able to work with the quantum computing and how that is being developed. So that's super exciting. What are the challenges you face in your research?
Well, so maybe I can talk a little bit about the quantum computing part of it, because so far we have been talking about classical cryptography, which we want to protect against the quantum computer, but hopefully we can also use the quantum computer to do something useful. And so these are actually the challenges that I face by being the director of QuSoft. QuSoft is a research center in quantum software. So we're trying to figure out what the quantum computer can and cannot do, and what is it useful for.
So what can it and can it not do?
Yes. So what we know is that we can break these cryptographic assumptions in the long run, but we will need very big machines for that. Our hope is that we can do something useful in terms of simulations. So we suspect, and that was also the original idea by Richard Feynman, why they would build a quantum computer in the first place, is that a quantum computer, a programmable quantum machine, is something useful to simulate quantum mechanical features that occur in nature or in materials or within our body. So there are a lot of systems out there that we kind of know that they are described properly by quantum mechanics, but it's just too complicated to understand, and it's even too complicated to simulate on a classical high-performance computer. So a lot of this high-performance computing time is actually spent simulating these kind of systems, but it turns out that it's still too complicated to actually fully understand. And when using a quantum computer to simulate these quantum systems, we have hope that we can better understand these processes, which could really have major impact in understanding these things, and therefore, for instance, making better fertilizers, so helping fight world hunger, maybe even kind of making better batteries, and this kind of, we can think of a lot of application in terms of designing material or designing molecules. So this is a very active area of research, and we like to contribute to that.
When was the first quantum computer created?
Well, of course, first somebody had to have the idea. So this happened in the 70s of last century, and then it was maybe, I would say maybe around 20 years ago when people really got the idea of of course, theorists had the idea before, how they could actually do this, but to be practically able to start implementing the system, that was maybe 20 years ago. And now there has been steady progress in actually getting more and more qubits. And the challenge is also to make it scalable, because we expect that useful quantum computers will be quite large. So maybe you need millions of qubits. And so it's not just putting a few of them together, but you will really have to have an architecture, a hardware, maybe a whole supply chain to have a lot of them. And yeah, this is ongoing research and ongoing development in this ecosystem, and it's really exciting to be part of that.
Can you give us some more perspective on your collaborations nationally and internationally?
Of course. So first of all, I'm the director of QuSoft. QuSoft is a research center for quantum software here in Amsterdam. We have about 100 researchers in total, maybe about 20, 30 permanent staff, and then a couple of postdocs and PhD students that all do research in this area. But we are one of the 5 main hubs of quantum delta NL. So funnily, delta actually, the Netherlands is a delta, but it actually also stands for Delft, Eindhoven, Leiden, Twente, and Amsterdam. So it forms the word delta. And we all collaborate in a big national program. The Netherlands have been very active pushing the quantum ecosystem with supported by a lot of money as well, which was great. So it allowed us to develop a lot of things. In fact, there will be a new building here built by the university just next door, dedicated to quantum. So that's very exciting for us. It also allowed us to start a new master program here at the university in quantum computer science that will actually start in 2024. Again, this sounds easy, but this has been a 2-year process to get this rolling. And of course, we also have international collaborators, so in the whole world, but in particular in Europe, we actually have EXI, so that's the European Quantum Software Institute, so that, of course, with a Q. And so there's a couple of people we regularly collaborate with, well, us here in Amsterdam, but then we have people in Paris, we have people in Latvia, we have people in Denmark, in Copenhagen, also people in the UK, and in Portugal, and in Germany. So yeah, we are researchers in this area are very well connected to each other.
As it turns out, we're both from Switzerland, und wenn sich 2 Schweizer im Ausland treffen, die Schweizerdeutsch können, müssen wir unbedingt Schweizerdeutsch miteinander reden.
Natürlich.
Christian, danke vielmals für deine Zeit heute, und ja, ich freue mich mehr über das ganze Feld zu entdecken, über mein Leben. Danke vielmals.
Merci.